So now I'm going to briefly go through who we are at Intech. So who is Intech? First, we're a value-added distributor, which is slightly different than just a distributor. So, and I'll get into that in a moment. We maintain a stock of materials to help keep your inventory flowing so you can get your projects completed, so you don't have to maintain the burden of all the overhead of materials. And our distribution portfolio includes Chance helicals and resistance piers, MagnaCore, hollow bar micropiles, Carbonbond, and the force arrestor wall bracing system in ISC. We also carry a number of other waterproofing and dehumidifying products, so feel free to reach out to us if you have a need for those. Our second role is a manufacturer. So we're the manufacturer of HydroWay, which is the fastest drainage system on the market that's been around for a long time. We use this system in a lot of applications, including basement waterproofing in lieu of a French drain or perforated pipe system. So a key principle of our business that I kind of touched on earlier is the value-added portion of our role. And our added value comes in two parts. For engineering, we can either be a supplemental value to help you grow or to be the first step into a new market maybe you don't have experience in. We have internal staff, Sam and myself, but we also maintain a wide array of different relationships with external consultants around the country, and they have an immense amount of experience in the specific industries we serve. And then the second form of value add that we provide is we have equipment. So we have a wide array of different rental equipment, as well as we can sell equipment that you can use to grow your business and also supplement your business. And we also have internal staffing that are trained on the equipment use and maintenance to make sure that you know how to use it and how to keep it running at its best. So Intech has two main locations, Caseyville and Livonia. These locations each have staff and stock materials that we use to get you what you need. I've also provided our main contacts for engineering, sales, and operations, so feel free to reach out to any one of us if you have any needs. And so I'll quickly go through our major brands. First, we have Chance, which is our helical and resistance pier manufacturer. They're the largest, most well-respected manufacturer of helicals and resistance piers in the world, for sure. Second, we have MagnaCore, which is our hollow bar micropile line that helps underpin and tie back a lot of different structures, walls, and slopes. Third, we're the manufacturer, like I said, for HydroWay and HydroVent. These are fluid and gas management systems, and it's basically a geosynthetic wrap strip drain that has really good inflow and flow through rates. And then fourth, we have Carbonbond, which is our carbon fiber reinforced polymer system, which I'll discuss today. And then we have the force arrestor brand, which consists of the wall brace system and the interior support column. And we're going to go through the wall brace system today. So here's an overview of the key players at Intech. If you have any specific questions about anything, technical questions, equipment questions, feel free to reach out to any of us and we'll get you pointed in the right direction. And one thing that I want to note is what sets us apart from other companies is how people focused we really are. Our number one goal anytime we have an interaction with a partner is to help you feel like family and make sure you get the materials and resources you need to be successful, because when you guys have a win, we all win together. So our first topic to discuss today is just some general discussions of basement wall construction and some things that happen to a basement wall in its lifetime. And so I'm going to start out with some basic terminology, and I'm guessing most of you are familiar with, these parts and pieces, but I'm just going to go through them real quick just so I know we're all on the same page. So on the left side, you have a floor slab, some footings that spread the loads out, walls that transfer loads and resist lateral loads, and floor joists above the walls, and then you've got your structure above that. So if you zoomed in on the right side, you can see that there's some sort of a connection between the wall and the structure above. And, it's not consistent makeup on every building, but this is the most typical form we see with a sill plate and a band board with joists. And there's typically bolts that are hung in the basement wall that stick up, and there's holes in the sill plate that slide over to make that connection. So basically, that wall is connected to that sill plate, and then subsequently the band board joist, and then the structure above. Then if you were to take this as a top-down view, and if you were to take off the subfloor and everything above that, basically, it would look like this. And so you have some of the same things that you could see before, like the footing and band board and joists. But one thing that I wanted to put in here also is, there can be some other things like a main steel I-beam spanning from one side of the structure to another, because those spans are pretty long, and you gotta have something rigid. And then there's usually some sort of an interior column if there's a really long span of that I-beam, so that it can span rigidly. And so one concept that can be important to understand is how everything is vertically loaded. So in red, you can see, if the subfloor were there, it's going to load these joists. So in red, you have the perpendicular joists, is what we call them. And these show the loads from the flooring transferring into the floor joists. And then those floor joists are going to be supported on either side, either by the main beam or the loaded wall. And then in blue, we have parallel joists. And these walls don't really get loaded up by the floor too much, and really only at the corners. And they're kind of loaded up from the floors as a result of the loaded walls at the corners, and also where the main beam is seated within the walls. Those are the two places that the floor loads get into it. So there's still forces from different weights and loads on all of these walls, but I just wanted to point out that this is kind of a typical setup for how the basement is going to look. So there are two types of wall construction that we see, on a regular basis, and there's others, but this probably covers about 95% of cases that we see. So the two types are a CMU block wall, concrete masonry unit block wall, which is a series of hollow blocks that gets placed on one another, and then they get filled with grout and reinforcing, and that creates the wall. And then on the right side, you have a reinforced concrete wall, which is pretty self-explanatory. They form up and pour continuously concrete that has internal steel reinforcing, and that's what makes up the reinforced concrete wall. So both of these types of wall in some way are connected to the flooring and above grade system in some manner. And the most typical type of connection, like I covered, is the sill plate, and it just has holes in it that slide over the bolts that are hung in the wall. And then that sill plate is connected to the band board, and then you have joists coming off of that are hung onto the band board or rim joist. And so then above that, you'd frame up your walls. And if you had a different type of construction, like if you had full masonry, the masonry would continue up. But I'm not going to go over that today. So when we start looking at this system, there are two forms of what we call driving forces going on. The first form of driving force would be vertical load. And this comes from things like the weight of the structure, some transient loads, and basically the loads are transferred from the above grade walls and the floors and the joists and down through the basement wall and down into the footing, where the footing then distributes that force into a pressure. But the other form of driving force that's going to be more important for our discussion today is the lateral loads. And so the lateral loads on a basement wall comes from a number of sources, most of which I'll discuss in a little bit. But there are also a few things that resist these lateral driving forces, which is mostly what we're going to be covering in the presentation today. And so the first point of resistance I'll discuss is the structure itself. So based on conservation of momentum, an object at rest wants to stay at rest. When you go to push something and it has weight, that weight wants to resist movement until the force is so strong that it overcomes the weight of the structure. And so that's an important part of what keeps the wall, the basement wall, what's called restrained. So it doesn't want to move inwards towards the basement. So another part of the basement system that resists loads laterally is the floor slab. The floor slab is usually several inches thick, concrete, and it's usually poured up to the wall. There are some other types of floor slabs that can be constructed that I won't get into today, but basically this slab provides a very rigid contact point at the bottom of the wall to resist lateral movement towards the inside of the basement. And there are also some other additional forms of resistance that we usually don't count on, but they can be important if you have a special scenario. So first, on the inside, on the left side of the footing, you can see those arrows. There's soil to the left of that footing that it can be, soft, but if it's stiff, it can provide some resistance for movement inwards. And basically, the thicker the footing and the stiffer the material, the more resistance we can likely count on. And the second form of resistance that is possible is the friction on the bottom of the footing. That can also help resist inward movement. And this will be a function of the area of the footing and the weight of the structure and also the soils that are there. So I've discussed some of the resistances, and now I'm going to go through the overarching concepts for what's behind the driving lateral forces. So first, the most intuitive form of lateral driving force would be the soil weight. And if you were to think about soil, it's intuitive to think that there's going to be some amount of vertical weight, right? It has weight. Generally, this weight, depending on the type of soil and how it got there, varies from about 100 pounds to 120 pounds per cubic foot, which is a density, but that's how we're going to talk about it today. So if you imagine taking, say, a 3 foot by 3 foot block of soil and you put it on the ground and you watched it, you'd probably assume that it's not going to maintain its shape. It'll probably fall apart, or at least it'll relax, but it won't completely run everywhere like a liquid. So this property of soil is how we can kind of develop the concept of confinement. Typically, a soil will relax, and when it relaxes, it'll actually distribute roughly 30 to 40% of its weight, of its vertical weight, laterally. So if we have a soil behind a wall that has somewhat, 100 to 120 pounds per cubic foot of vertical weight, we can assume about 30 to 40% of that weight will be felt laterally by the wall. Okay, so other than soil, there can also be a number of other things that can have an effect on the stresses behind the wall. And the biggest thing that I see that can have an impact on below grade walls is water pressure. And so within a soil profile, there can be a number of sources of water. And the first source of water that I'm going to discuss today is the groundwater table. And if you're not familiar with it, the groundwater table is a general part of the soil profile, basically where the soil below that point is all going to be saturated. There's just some amount of level of water that no matter what, if you dug a hole in it, it would fill up with water. And so this can exist anywhere within the soil profile, or it can even exist above the soil profile, and that's usually how you get something like a pond. And it can also fluctuate throughout the seasons of the year. So you might do an exploration and find it at 5 feet, at one time of the year, and maybe it's not even there if you dig 20 feet, later on in the season. So it can exist. You got to make sure that you're aware of that. And so same as soils, we can think about taking a 3 by 3 block of water and put it on the ground. And obviously the block of water isn't going to hold itself up at all because it's a liquid. It'll just run everywhere. So with that same concept as before, since it will run everywhere, it will put all of its pressure laterally per its weight. And water weighs approximately, its density is about 62 pounds per cubic foot. So a number of other sources behind a wall can occur for water, and that includes things like runoff, seepage, poor water management. So if you don't, put your downspouts out to the street or something like that, all of these things can have superficial sources of water, which can be problematic. And so I'm going to start out by making a blanket statement about water. As a geotechnical engineer, the change of water in a soil profile is probably the #1 cause of structural performance issues across the board. And this can be in the form of water being lost out of a profile or water being gained into a soil profile. And for today, since we're talking about lateral forces, most of the time I'm going to talk about gain of water. So water does two things behind the wall. First off, it adds pressure to the wall, which I discussed in a couple slides ago. All of its vertical force is also going to be transferred laterally into the wall. But the second thing that it kind of does is it creates this float of the soils, or creates a buoyant force in the soils. And this actually reduces the vertical weight of the soils. And this decrease in the vertical weight also decreases the lateral weight. So you might say, okay, well, that makes it better to have water behind the wall because it's making the soil lighter. But typically, the decrease in that lateral soil weight is outweighed by the increase in the water pressure. So you might lose 20 pounds per cubic foot in the weight of your soil, but you're going to gain 60 pounds per cubic foot from the water. So this is really, important. You don't want to have water impounded on your wall, or you need to add extra reinforcing into your wall to account for it if you have a constant high water table. So there are some other things that can happen behind a wall. This slide shows a layer that can exist called frost depth layer. And if you've done construction, you know what this is. It's basically a layer that's a few feet of soils that seasonally within usually winter, you'll have cyclic freezing and thawing of water within the soil, and it builds up ice lenses with depth that build up further and further down into the profile. And you can have, frost sensitive materials near your wall that start to have this buildup of ice lenses, and it pushes laterally on the wall, and it can exert forces to break the structure. So another scenario that can be detrimental is having nearby trees. In cases of extreme drought, when water is scarce, the root systems expand to try and find more water. This can happen where the roots go deeper, but it can also happen, where they go laterally. And if you have, poor fill next to your building that's loose, it can pool some water, and that can be a really good spot for the roots to get a lot of water. So they'll really get in to that spot and push laterally on your wall. And I don't know if you guys have ever seen it, but there's pictures of trees breaking huge boulders, and concrete is no match for a root system. So, one piece of wisdom is if the root zones of trees are typically bigger than what you can see above the ground. So, even if your tree isn't close to touching your building, it still might be close enough to have an effect. So make sure you're keeping track of that. So how does an engineer think about all these driving forces and resistances? And basically you can turn the scenario of the wall on its side and generalize it and consider it to be a concrete beam. So if this beam right here is a rigid concrete block and it's supported on either side, that's kind of a representation of that wall. And so one side you can consider that slab, and the other side you consider the weight of the structure. And it doesn't really matter which side you consider. But so now if we were to take that scenario and apply the driving forces from the soil pressure and the water pressure, you can imagine, well, what's going to happen? So whenever you put, a load on anything, it has strain. And generally, since the supports are there, it'll bend and flexure along the length of the beam. And this obviously isn't to scale. A concrete beam it's not going to deflect very much without breaking, but I'm just exaggerating it so you can see what's going on. So if we zoomed in on what's happening at the top and bottom of the beam, we can see two things happening. So if you looked at the top line on the top side of the beam in red, that line kind of contracts. It gets closer together. And so we consider this to be what's called compression. And then on the bottom side, on the bottom line, where it's blue, that line actually expands. And we consider that side to be in tension. And one feature is that it performs really, really well in compression. You can load it up really, really high. However, in tension, it performs really, really badly. So tension for concrete, somewhere on the order, it's under 10% basically of its compression strength. It's like 7 or 8. And so, for most designs, having a purely concrete beam as your wall is not going to perform well. So how do we address this? We add reinforcing. And so we add reinforcing steel bars, and we also add them in line with the loads that are happening on the beam. And that provides strength to that side of the wall. So now if we were to rotate that beam and put it back into the design scenario, we have this scenario. You have your two resistances on the left side, you have your driving forces coming in from the right, and you have a concrete beam. So the tension face of the wall is going to be on that same side of the supports, which is the opposite side of the driving forces. And so you'll typically find at a minimum that there will be reinforcing on the inside portion of the wall to bolster, to increase the strength of the tension face of that wall. But sometimes that's not enough. So now I'm going to go through potential problems that can come up over time in a basement wall from a lateral standpoint, and then we'll go through all the other fixes. So this slide shows the three general forms of failure in a wall system. You got bowing, tilting, and shearing. And one note I want to make is, and I'll probably say this a bunch of times, these are individual failure modes. Multiple types of failure, laterally and vertically, can occur on one wall. And it's important to figure out why the wall is performing badly to determine the proper fix, and to determine all the possible failure modes that are happening and could happen in the future. And it's really important to have somebody experienced assess the structure and determine what that fix will be. So here's a couple different views of each of the types of failure. The first one is bowing. You can see on the left side, you have a break towards the midpoint of the wall. This will happen at the midpoint usually or lower. And this is basically a point of concentrated stress that causes a horizontal crack if you're looking at the wall. And it usually happens across most of the basement, and usually it spiders out at the corners to each extent. And this can happen on either reinforced concrete or CMU block walls. Usually the crack will hug the masonry lines, mortar joints for the CMU block walls, but it'll spider up. So here's the second type of failure, which is tilting. You can see the wall is rotating around either its connection point at the footing, or the whole footing can rotate with it. And this is more common on a reinforced concrete wall because it's more continuous. Usually a CMU wall will probably have a shear failure before that. And so one important thing to watch out for is this form of failure can also result in a disconnection between the top of the wall and the structure. And this connection needs to be probably reestablished in some way, which I'll talk about in a little bit, to make sure you can provide that resistance point so the design is going to be complete. And so then this is the third type of failure, which is shearing. And this is when a horizontal failure occurs across the wall, and you have an intact portion above an intact portion, and they just move differentially from one another. And usually it happens with that top portion moving over the bottom portion that's staying in place. And you can kind of see that here. You have your intact portion pushed over the lower portion. And these types of failures are more common in block wall construction, and most of the failure happens at the mortar joint, a couple blocks up. And so this type of failure also doesn't usually happen in poured concrete walls. So I wanted to take these next two slides and just kind of give you a couple important notes. For the homeowner, you need to get the structure assessed and geotechnical conditions figured out to determine why something's failing. This assessment should be communicated and followed up with a repair solution being recommended. And you got to know that if you don't take the recommendation, you shouldn't expect the system to perform long term. You shouldn't expect your contractor to stand by something they didn't give as a recommendation. And basically that's trying to say, if you're going with the bare minimum, there's going to probably be further fixes down the road that need to be completed. So for the contractor, the most important thing you can do in your business is to document everything. Document the recommendation you made, document promises, document what was purchased, document what was installed, and anything that kind of happened during construction that's important. And if you don't do this, you're potentially taking on financial risks in your business. Keep records. It's not too hard, and it'll serve you. So another concept that's important to discuss before we get into the actual fixes is, what's the difference between an active and a passive system, and which options go under which style. So what I generally describe as an active system is something that can be used to reverse movement that's occurred in the structure. So for our portfolio, I classify our most active system as tiebacks or dead man anchors. And I'll kind of get into these in a minute, but these two systems are installed basically past the wall, deep into the soil profile to a soil that is going to be used to bear the loads. And these two systems are usually a little more costly than the other two, but they're usually the most versatile and will perform a lot better and will have a lot better ability to recover movement, which Sam will discuss later on. So the next two types of systems, and the ones that we're going to really dive into today, are more economical, but they do have a little bit of limitations. So I'm going to skip, and I'm going to talk about a passive system first, because that's the other end of the spectrum. And basically, a passive system is a repair system that really doesn't do anything to recover movement. This system adds strength to the support side of the wall, but it doesn't do anything to really push it back. And our Carbonbond system would fall into this category. And you basically attach it to the wall, and it'll add flexural strength to the wall, but it won't cause that wall to move backwards. And then now I'll talk about the intermediate system. And I kind of consider this an intermediate system just because it does have some limitations in the amount of movement it can recover. And there are some scenarios where you might not be able to use it, or it could be problematic if you used it. So the intermediate system is still a system that adds forces to the wall and will recover some movement, but have some limitations that we'll discuss in the force arrestor portion. So the force arrestor falls into this category, and there are specific scenarios that we'll talk about. So this is just a graphic representation of where each of the systems falls on the active to passive scale. Tieback's on the left and Deadman on the left, and then Carbonbond further on the right with passive. And there are some scenarios that you can't use or can use each of the systems. And just important to note that Carbonbond is typically either for crack repair and sealing for waterproofing. You could chase a crack and really seal up the crack, or you can use it in vertical applications for a bowing wall. But it really won't do much or anything to repair or add strength for a tilting failure or a shearing failure. So then force arrestor can be used for bowing, tilting, and some shearing, which we'll talk about in a little bit. But you can, if you have a moderate failure, you can use the force arrestor to strengthen and recover movement. And then the tiebacks for Deadman, this is our, probably most versatile, adaptable system. And this is a system that you could use for all three of the options. So I kind of went through an overview of the tiebacks and Deadman, and I'm going to go into it just real quick again. You can see on the left side, there's a steel bar that comes into the structure from the right, from off screen, and it has a nut on the inside of the wall that bears on a plate. And past the extent of the graphic, basically there's the steel bar continues for 20 feet, depending on how far back you need to go to get to competent material. And it's either got a plate or it's got helical flights that are buried and screwed into the soil way past the basement walls. And so the implication of this is you can turn that nut and it'll create a force onto the plate, and it'll push that wall back towards the soils that are causing it to fail. And this system, you can marry it up with beams, you can marry it up with channels, and you really can use this system to pull back walls with pretty substantial movements without having to jack up the building. There are some things that you might have to do to relieve some pressures to get it to work, but it's really adaptable. So now I'm going to go through the design principles and installation for Carbonbond, what Carbonbond is and what it's used for. So what is Carbonbond? Carbonbond is basically our system of what's called carbon fiber reinforced polymer, or CFRP, that adds additional tensile capacity to a structural member. And it's made up of two main constituents, the carbon fiber and the resin. And there are some specific benefits to using these specific materials. There are other types of FRP materials, but carbon is one of the best. So for carbon fiber specifically, it's very strong in tension, and it's quite a bit stronger than steel, usually 4 to 5 times at least. Additionally, carbon fiber is a fabric. You can mold it, you can form it, You can custom fit it around something and customize it. And then carbon fiber, it doesn't do so well in shear, so you can actually cut it with sharp scissors, which makes it pretty easy to manage and cut something custom. So then resins, basically they're the glue of the system, and it's the main function from a structural standpoint, from a strength standpoint, is to adhere the carbon fiber to the wall, but it's also got some other secondary benefits. It'll seal the system from water, it'll protect the carbon from weathering, and overall it'll make it a much better product, and it's necessary. So there are a number of different applications other than residential basement walls that CFRP is used for. These are listed at the bottom, and these are more commercial, but if you guys have a need for that, we can help support you with that. So this slide shows some of our engineering properties for our current lineup of CFRP. You can see our carbon is relatively heavy, which gives it a lot of strength, but we are also evaluating other unidirectional options. Our current is also biaxial, which basically means that it's strong in both the longitudinal or along the length of the fabric dimension as well as across its dimension. So our current fabric is strong both directions, but we're also evaluating other unidirectional options. So here's a picture of our resins. Basically, you have a part A and a part B. When you mix these together, it'll harden to create a glue. You have about 20 minutes of hot life and then 35 minutes to gel time. And basically, after that point, you can't use it anymore. And this resin, once you mix it together and you put it up on the wall, which I'll discuss in a minute, it creates that glue that sticks the carbon fiber securely to the inside of the wall. So let's revisit this design scenario. We have a wall, it's been constructed already. It's got reinforcing in there. We have our support points at the top and the bottom of the wall. We have driving forces. And like I said, we have the reinforcing. So maybe this system, maybe it's okay as it is in the ground for 10 years, but one day something breaks, and you might ask, why would this happen? And basically, things aren't constant. Sometimes loads change, sometimes structures weaken, and, it is what it is. The as-built construction isn't sufficient to carry whatever loads are on there. And maybe that's something that happened one time and won't ever happen again, but it could be something that, could be sustained after a while. So instead of only counting on rebar, you can add Carbonbond to the tension face of the wall. And, this will add more flexural strength and recover a lot of flexural strength you might lose by adding this. And it's a retrofit system, so you can install it after the structure's already been built. There's also carbon rebar that you can have if you wanted to put that into your wall to begin with, but you can add this as a retrofit installation onto the inside of your wall to add to the flexural strength. So, you basically take these strips and you install them on some frequency, and the strip frequency or spacing depends on a number of things, and we will have marketing collateral that we can get you that kind of gives you an idea of what type of wall, what kind of backfill, how high it is, and this is the spacing that you should use. So you don't have to cover the full face of the wall. You basically count on those intact portions of the wall to transfer some of the stresses into the strips, and then at that point, the Carbonbond will transfer the loads across and add your flexural strength. And like I said, it's usually on the order of 2.5 to 5 feet on center. And one other note is, if you're installing around windows and doorways, you need to treat it a little differently. You need to, add around those openings, because you want to add flexural strength to those points where there could be potential stress concentrations from the corners. So just wanted to show a few as-built, as-installed pictures of Carbonbond in a couple of residences. And I think, one of the big takeaways from these pictures, as you can see, is it doesn't protrude at all into the space. And in this case, you can barely even see it. You can actually paint over the system and really hide it. So that's usually a pretty good selling point for the system. it'll add strength, but it'll also be pretty much invisible. So now I'm going to go through the steps of installation, and let's just say this is our wall failure. You have your bowing wall with the crack, kind of in the middle all the way across, and you want to put up some Carbonbond. So the first step is going to be you want to perform crack injection. You want to treat your crack, make sure you're sealing it so that water isn't going to be seeping out into your basement. You could do this, with epoxies or resin or however you want to do that. You could also put in Carbonbond over the crack and seal it up. So one other note is you need to also be performing any concrete repairs and address any corrosion in steel if there is any. You need to do that before you install the Carbonbond. So the second step is probably one of the most important steps of the whole installation of the system for its performance. In this step, you're basically preparing the surface at the strip locations by scarifying the wall. You're going to sand it down. And it's so critical because one of the most important things is the bond between the carbon fiber and the wall. And if you have, anything between the substrate, which is the wall, and the Carbonbond and the resin, it'll create a weak point. So you would be wanting to remove any oils, you remove any dust, paint, and just dirt. Those are just, really easy things that can inhibit a bond and cause the system to have a failure prematurely. So you got to clean it all off. You got to have it down to pure concrete. And so we just want to scarify the wall. You want to, if you were to look at the wall, if you're asking about how much you got to scarify it, if you were to look at the wall with a microscope, we want to achieve a 5 mil profile, which is 5 micrometers between peaks and valleys. So it's really smooth. You also want to make sure there's no fins or sharp edges or protrusions that could cause there to be air bubbles behind the wrap. And you also, as just a general note, you want to scarify beyond the extents of where you plan to install the carbon fiber. So you don't want, if it's a 6-inch width strip, you don't want to scarify 6 inches width. You want to scarify 8 to 10 inches just to have a little bit of extra room in case there's a little play in your install. So just to reiterate, this is one of the most important steps to the system. So step 3, you want to mix your epoxy or resin. You want to mix it with whatever ratio, which ours is a 2-to-1 ratio of part A to part B. And in our kits that we sell, which I'll show in a minute, we have these pre-measured for the amount of carbon fabric roll within the kit. You have to another important thing to pay attention to is you got to have the amount that you plan to install installed before the pot life is up, that 20 minutes. You need to have everything up on the wall for the portion that you're planning on installing. So you might work, 3 strips at a time or 1 or 2 to get it up there. And you just need to have it up there. Otherwise, it'll not perform over time. So step 4 is to roll up a layer of saturating resin to the stretch of strips that you're planning to install. You want to roll this up in the area the strip is going to go. You also want to, like you scarified beyond the extents of the carbon fiber, you also want to roll beyond the extents a little bit, so that just in case you have a little play. So then on the floor, on like plastic sheeting or whatever, you can apply some of the saturating resin to a pre-cut section of the strip. That's the height of the wall. And you're saturating the strip while it's on the ground, so it should be fully wet when you go to place it up on the wall. And here's a picture of that, just rolling it on there, saturating it, making sure it's really wet. So then you take your carbon fiber strip, you put it up on the wall, and then you roll over to fully saturate with saturating resin, making sure you're rolling out any air bubbles or anything like that. And just a rule of thumb, you want epoxy coming out of the sides of the carbon strips as you're rolling it. And then here's a picture of somebody putting it up on the wall. Pretty much the same thing. So then you just repeat these steps 1 through 6 at all the locations that you're planning on installing for your structure. And at that point, the system will become tacky 30 to 60 minutes with our resin. It'll have an initial cure in 3 to 5 hours, and it'll fully cure within a day to 2 days. So after the system is fully hardened, the installation is complete. And at this point, you can paint it or apply protective coatings. And if it's desirable, if you want to paint it or apply coatings, you might need to slightly scuff the surface so that the paint or coating bonds to the resin. Otherwise, it might flake or peel off over time. So there are some things to avoid based on the resin. You don't want to install outside the temperature ranges of the resin. You don't want to apply to really fresh concrete, so 30 days old, 28 days old, somewhere in there. You don't want to apply if it's younger than that. You don't want to apply to concrete with curing or sealing membranes because it'll inhibit a bond. And you don't want to apply to concrete when the concrete temperature is less than 40 degrees. And this slide shows what a kit of Carbonbond is comprised of. And this kit basically represents, a couple 8-foot long strips with the right amount of resin to get it all rolled up. So you can order this kit and you can come out with a number of kits to install, and it just makes it really seamless. So now I'm going to hand it over to Sam. I think he should be able to knock it out in time. So how much time do we need here? I think we got about 8 minutes. Yeah, 8 minutes.
So we're going to cover the force arrestor wall brake system portion of our presentation now. So what is the force arrestor wall brake system? The force arrestor is a wall brace system which provides support to an existing wall that is undergoing distress and apply a limited amount of active engagement to that wall. And the system is basically comprised of 3 main components. You have the beam, which spans pretty much the full length of the wall, a bracket at the top which connects to the floor joists, and a toe nailing system. So like I just talked about, this is kind of a graphic demonstrating the 3 main components. So at the top is the bracket, which is connecting to the floor joist, and then the beam spanning the entire length of the wall, and then the toenail fixing it at the bottom point. So the main thing that Sean was talking about earlier is sometimes you can lose the connection to the top of the structure. So a key component that this system provides is reestablishing that point of connection to the structure at the top. To help improve the resistance or the resistive forces that you need to resist those driving forces. So as Sean talked about earlier too, there's 2 main wall types. You have a wall that the joists land perpendicularly, and then a wall where the joists are running parallel to it. So because of this, you basically need 2 different types of bracket connections that we come up with solutions for both. So on the left here is an image of the perpendicular wall brace system, and on the right is an image of the parallel wall brace system. And we'll dig into both these a little bit more, but these 2 images just sort of have a good representation of what the systems look like. So for the perpendicular wall bracket, as you can see, the joists land perpendicular to the wall, and the main thing here is since the joists are perpendicular to the wall, these forces can actually be resisted in plane, so you can bolt directly to the floor joists to resist these loads. And a key thing here is we use 2 joists to connect to our system, which spreads the load over 2 separate joists, reducing the possibility of failure, and it's just a better connection approach. So for the parallel joists, you can't just load against the joist like you can for the perpendicular system, because you'd be loading up those floor joists along the weak axis. So you have to, ultimately you have to add in kind of an artificial perpendicular joist by blocking between the parallel joists. And typically you need to span a minimum of like 4 joists back with your blocking. And in some cases, you may run into a situation where you've got some duct work or electrical work, plumbing, or anything else that may be in the way, like in this image on the left. And in those cases, you can just put that piece of blocking kind of flat and flush along the bottom of the floor joists. But typically, upright, like a traditional floor joist, is going to be the best approach for this blocking. And essentially, what you're doing there is you're taking that force on the weak axis of the floor joist and spreading it over multiple joists to make sure you're not going to hinder the actual structure in any way. So the typical spacing for the force arrestor wall brace system is 3 to 6 feet. There's some key things that will determine what kind of spacing you're going to need. And that's going to depend on how high the wall is, the type of wall construction, the wall reinforcing and thickness, the backfill behind the wall, the groundwater table, and the amount of deterioration of the wall. So this is another image, the same image of that perpendicular system, but we're going to go into the installation steps. So the first thing you're going to do is, look at those conditions you have with your structure and establish your spacing. And once you've got your spacing, you're then going to lay out your planned beam locations on the wall. You can mark that, however you want, but the first step is going to be marking those locations. So once you've got your locations marked, you then need to make a custom fit for your beam for the exact, wall height you're going to need. So you're going to need to, and I think it shows on this next slide here, you're going to need to allow just like maybe a couple inches off the top of the joists to really span as much of the length as you can. So then once you've got your locations marked and your beams cut to length, you're really at this point ready to begin installing the system. So the first thing you're going to need to do is kind of loosely bolt your components together and mock them up into place. And the important thing with the perpendicular system is there's a left and a right side bracket, and then that center span piece. And technically the left and right side, you could use two left or two right pieces, but the way our system is designed, for installability reasons, it's easier to install it if you have the correct pieces for the left and right. So once everything's loosely bolted together, you may need to clamp the bracket to the joists and use it as a template for drilling your main holes. And in the perpendicular system, there's going to be two 5/8 inch holes you need to drill in both floor joists. So at that point, once you've drilled your holes, you have everything where you want it. You slide your bolts through and tighten the bolts for the side brackets. And then once everything's in place, you've got the side bolts tightened up. There's some slots for adjustment on that center span, and make sure you've got it nice and centered, and then tighten down those two bolts for the main center span. So at this point, all we're missing is kind of the connection to the floor, and we do that via the toenail, which is basically an angle piece with two 5/8 holes for concrete wedge anchors. So once you have it in place, drill out your holes, hammer those wedge anchors into place, and tighten them down. And then repeat this step at all the other locations you have marked, and you basically have the wall ready for the final step, which is applying the torque to the bolt, which is actually what Sean was talking about earlier. It's kind of an intermediate engagement into the wall, so it is active, but you're not going to get the same level of active resistance you can get with like the tieback system. But again, the last step is to torque your bolts to really kind of actively engage the system with the wall. And at this point, your installation is complete, and your wall is now reinforced with the force arrestor. So for the parallel situation, and again, we talked about this already, but the first step is going to be determining your spacing and marking your locations on the wall. And similarly to the perpendicular system, again, you're going to need to cut the beams to length. You do the same rule of thumb where you're just a couple inches from the top of the joists to really engage as much of the wall as you can. And then you'll add your blocking. And again, you may have to get creative with this, but we like to see a doubled up blocking between the joists, at least 4 consecutive floor joists back. And there is not going to be any blocking between the last floor joist and the sill plate. That's going to be the gap where the beam is going to be located and your bracket's going to be pushing on it. So once you've got your blocking in place, you're then going to want to install the bracket to the blocking. An important part to this is ensuring that the bracket is engaged on both the plate on the one end and the angle on the other, so that there's no chance of rotation whenever you begin to torque it and the wall starts loading it. because if you don't have a good engagement of the bracket, there is a chance the bracket could rotate, which is definitely not desirable. So, and this is kind of a better angle of that. And once I'll go into it more once we have another picture of the bracket on the screen. But it's really critical that the plate side and the angle side are both snug against your blocking, so there's no rotation. And make sure you get those two bolts really good and tight on the bracket itself. Like I just talked about, there's two bolts for the parallel system that go through the blocking. You're going to need to get those bolts in there and tighten them up. And then you do the same thing with installing your concrete wedge anchors at the bottom of the beam to establish that point of connection. And then the last piece is going to be installing a steel reinforcement strap along the bottom of your blocking, starting at your bracket back. And this kind of makes your blocking kind of behave as a composite piece rather than 4 pieces of independent blocking. It creates it more of a unified system. And once you've got the first one done, the next step is going to be, do the same thing at all your other locations. And then you've got a system that is completed and a wall that is now reinforced. Now, and again, the last step again is similar to the perpendicular, where you torque the bolt, which kind of begins the process of actively engaging that wall again. So, and here's a photo of a real world application, and you can see in this photo, this is a perpendicular setup where the spacing in this case was about 3.5, 4 feet, a little tight, but this was a tall wall with a lot of backfill, and it was kind of at the maximum extent of rotation that we can use this system with, so the tighter spacing was called for in this case. And similar to our Carbonbond, we sell the force arrestor as a kit, basically having everything that you're going to need. You're going to have your support beam, your left and right side brackets, your center span, your top beam connection. And I didn't talk about that much, but piece 4 there is how you actually make the connection from that bolt to wrap it around the I-beam. And then you have your toenail, it's piece number 5 there, which sits underneath the beam, fixing it. 6 is the bolt, which you use to actively engage the wall. And then 7 through 12 is a hardware kit that's provided with each system. So if you buy a kit from us, you can expect basically everything you're going to need to get going except for the tools. So similar to the perpendicular system, the parallel system also has all the components you need. The components are a little bit different though. Again, you have the same 9-foot support beam, but in this case, we also have that blocking reinforcement strap to make the blocking behave as a composite system. Then you have the parallel bracket itself, and I told you guys I would talk about that a little bit more. So, and you can see on both sides, there's a plate and an angle welded that basically need to be snugly placed against the blocking, or the system will not perform, as you expect. And the height of that on both sides is the same. You press it snugly against before you drill and install it. And then in this case, the through bolt that you use to tighten it is actually a longer bolt, because you end up, when you install these, because of the nature of the geometry, you end up needing a longer bolt. So you can see the bolt for this system is a little bit longer. You have the similar toenail piece, and then again, a hardware kit down to the wood screws you need for your blocking reinforcement strap, so that all you need whenever you get a parallel system is the blocking itself, and again, any tools that you're going to need for the installation. So now kind of some overarching basement wall decision-making tools, or tips and tricks. Because what type of structure you're working with and what type of failure you're working with is ultimately going to lead you to the best mitigation effort that you can. So for tiebacks, and I'm not going to go through each one of these just for time's sake, but for tiebacks, kind of the main highlight benefit is versatility in almost any type of structure and any failure mode as well. and it's a fully active system which can recover most of, if not all of the movement that has occurred. And the main hurdle that you're going to encounter with a tieback or deadman system is that it's really kind of the most expensive, time-consuming, and intrusive approach to the structure. But again, that's usually outweighed by the benefit of being used in any type of failure mode, which leads you to if you've got a 5-inch movement, you're probably going to be tied to just this. So for the force arrestor wall brace system, some of the main benefits are it's very low destruction to the structure. You're going to be drilling a few holes in your floor joists, which really shouldn't impact the structure at all. And you can typically install an entire basement in either 1 or 2 days. And then the main hurdle you're going to encounter with this system is it cannot be used on certain structure types, such as like walkout basements, or with structures that have excessive movements, usually in the order of 2.5 inches or more. This system is not going to be, the best in that case. So for Carbonbond, again, the main benefit is similar to the wall brace system, where it's non-destructive to the structure, and it really doesn't intrude into the space at all. It's virtually like a piece of paper on the wall. You paint over it, it's not there. And again, these can typically be installed in 1 to 2 days, just like the wall brace system. So they're in and out of the customer's home quickly. And then the main hurdle you're going to have with Carbonbond is that you're limited to small structure movements again, and you're also limited to strictly a bowing failure, not tilting, not shearing. You're only going to be able to use this for a bowing failure. So, and Sean talked about this earlier, typically when you have a lateral failure on a wall, that's usually not all that's going on, and you may have to pair it to some type of vertical system. And I'm not going to go through these, but these are some of the vertical systems that we offer. And again, Sean also alluded to the point that, when you have lateral failures, vertical failures, if you only address the symptoms and you don't address the cause, you're probably not going to have long-term success with your efforts. So managing the water, which is usually the cause and not the symptom, is going to be beneficial. If there is no water management in place, I would consider looking at managing that water as part of the solution. And here's some of the water management solutions that we offer. And again, if you have any desire for any of that, you can just contact us and we'll talk to you about it.